All right, ladies and gentlemen, class recording gets started. So, in the previous two sections, we talked about oscillations. We talked about periodic motion, a motion that repeats itself. And we talked about the characteristics of that periodic motion, right? It requires a restoring force, something to bring it back to where it started. And then we talked about how we describe that motion. Period is the amount of time that it takes. Frequency is how often it happens. Amplitude is how far away from the equilibrium position it goes, et cetera, et cetera, et cetera. Okay? Now, the thing is that these oscillations, this periodic motion, rarely happens in isolation. What happens a lot of time is that periodic motion, that back and forth, right, then causes effects in other places, in other things. And when that happens, the energy of that motion, because there's energy associated with it, kinetic energy because it's moving, right? Also, gravitational potential energy, if you talk about a pendulum, right, it goes up and comes down. Or if you talk about the mass on the spring, the rubber bands in the cart, we have elastic potential energy thrown in there as well. Go ahead, hon.
Does all energy like move in waves?
No. So good. I don't know if you guys heard the question or not. Hannah said, does all energy move in waves? And the answer is no. Sometimes energy moves with matter, right? Like here, remember, our energy is our ability to do stuff, right? The ability to change things. So right now, my breakfast has the ability to change stuff because now I have energy, quote unquote, right? So, but I can take some of my chemical energy, which is my breakfast from this morning, turn it into kinetic energy by doing work on this ball, right? Then the energy is carried by the ball from here to there and can result in the shelf breaking or whatever it might be. Does that make sense? So matter can carry energy, but energy doesn't need matter to carry it, not in all cases. And so that's where that actually is a good transition into what we get into today, and that's where we get waves from.
So,
Okay?
So basically, if I had it all thought out in my head, like,
Okay, so to answer your question, does energy always travel in waves? No. Sometimes we can actually have matter carry that energy from here to there, but sometimes we have waves can carry that energy from one place to another. Okay? Cindy, you ready?
yeah.
Why don't you go over there? Demonstration. So. All right, hold tight, please. No, don't put your finger through it. Just hold it, with your hand.
Hold it?
Yep. Okay, so take 2 steps back and go all the way to the wall. Okay, all right, so here we have this spring, right? And the spring has the ability to transfer energy from one place to another. But in order for that to happen, I first have to give energy to the spring. I have to do work on this spring. And, I don't know if we remember or not from our work and energy chapter, in order for us to do work, we have to do 2 things. There are 2 requirements for work to happen. Do you remember what they are? Force and? Yep.
Force and momentum.
Distance, right? So I have to apply a force to something, and then that something has to move because of my force. So I'm going to apply a force down here to this end of the spring. I'm going to move the spring, and that will be work done on the spring, right? Hold tight. Ready? Here we go.
Oh my God, that's so cool.
Wow.
So,
It did that.
say again?
It did that.
Yeah, that was awesome. Can I please?
Wow.
Hey, look, it's a sine function.
It is. So,
LOL.
hold on to that for just a second.
Alright.
So we're gonna end up. It's a sine function, so it always starts at 0.
Woo!
And ends at 0.
All right.
Wait.
So, as
Or
far
does
as
it
the work is concerned, you can do it that way if you're good.
Oh my god.
Oh my God, if I could just...
I know that it's already like said that energy exists and it's always existed, but like creation?
Other than the Big Bang? No. Like, that's, yeah, it's just, it's a ever since the beginning of the Big Bang, energy has just been transferring from one into something else, you know? Now, what is energy? That we're still kind of working out, right? That's when you start getting into like string theory and stuff like that, you know, and I'm not ready to do that just yet.
Okay, but say if the Big
I
Bang
can go
Theory
with
were
that.
to happen again,
Yep.
would you say that energy was created? Because I know you can't
Well,
say that.
so I guess that's when we talk about energy never being created or destroyed, we talk about it in the context of our universe, because the evidence that we've gathered suggests that nothing existed before our universe, and so energy was present at the beginning of the universe. Does that mean it came from somewhere? Who knows? You know, like it was just there already. Does that make sense? All right. Question up.
My truck is.
Oh, hold on. All right, so let's talk about what just happened, okay? I did work on one end of the spring. I applied a force to move it a certain distance. And then, because these spring coils are connected, right? If I do work on one coil, as it moves, it affects the next one. And then as the next one moves, it affects the next one. And so on and so on and so on and so on, all right? So, kind of a little bit different than we talked about before. This energy is traveling through matter, but no matter is actually going anywhere. This coil of the spring doesn't end up down at Cindy, but the force and the energy and the work that I did to this spring ends up on Cindy's hand, because when I do this, her hand moves a little bit. Right? Okay? So, while matter is involved in this transfer of energy, no matter is actually going anywhere. It just kind of hands it off one to the next to the next. Does that make sense? And that is what our definition is of a wave. Well, it depends on a couple of things.
Here's another question. If it were to carry on, like if you were saying that waves pass it on to each other,
Yep.
wouldn't some energy be lost?
Yes. And that's why what eventually
Lost in my
happens,
hand, right?
what
I mean,
eventually
lost in my
happens to this wave that I created, right? We gave it a word the other day. Do you remember the word that we gave it? What do we have? It's damping, right? So what happens first? So this is jumping ahead, but we'll go with it, right? Okay. So here, okay. So pay attention. And if you're watching the video, sorry, I can't see this, right? So here's one wave, right? Right. And then here's another wave. Here, pull that. And then here's another wave. All right, ready? Start. All right. So what's the difference in those two waves? Let's use some vocab.
Amplitude.
Amplitude is different, right?
Period.
So
Crest.
period is not different.
Crest.
Okay. So crest, trough, those relate to amplitude. We'll learn those words a little bit later on.
Oh,
So,
frequency.
now, frequency, right? This one's a little hard to talk about frequency because I just made one wave, right? So it's kind of hard to say that there's a frequency to those waves. Let's stick with amplitude first, okay? So amplitude, we learned in the last chapter, is the distance away from the equilibrium position that an object moves. What causes the amplitude of this motion? Not the force,
The
but
amount of
the what?
energy that's put into it.
The amount of energy that's put into it, because it's the force I applied, but also more importantly, the distance that I move my hand. The disturbance of my hand, or the work done by my hand, determines the wave that is created. So the amplitude relates to the energy of that wave, right? So higher amplitude, more energy, lower amplitude, less energy. And Cindy, you can tell when it hits your hand, right?
Yeah.
Like, you know, this one moves your hand a little bit, right? This one moves your hand much more.
Yeah.
Okay? So, come go.
If Cindy wasn't holding on to the other end, it wouldn't come back.
It would, actually. Yeah, well, that we get to the end of that. here
It
in a
would?
second, so, yes.
But
Here,
would
you
it
want to see?
No, it won't. It'll just go away like here.
Nope.
Like this.
Here. Let it go.
Let it go.
There. I'll come over here so you guys want to see. You're not gonna do this on the floor.
Oh, well, yeah, that way. Look at this. I mean, yeah.
Everybody ready?
Wait, do it sideways. It worked freshman year.
Do you want somebody
Oh,
to
wait.
hold it?
No, you want to try it without full.
What? What was that energy that comes back? The one that, okay, is lesser than the one that you have?
Okay, so the whole point of that discussion we were getting into is that the energy of the wave that comes back is less than the energy of the wave that I sent, right? So we refer to that as damping. And what effect does damping have on the wave itself? It causes a what? A reduction or a decrease in the amplitude. Why does that happen?
Loss of heat or heat energy transfer.
Heat loss because of friction, right? Also, too, you can hear it. Sound is a type of form of energy as well. So it's continuously losing energy as it goes through the other stuff. Okay? But what we talked about, in general, waves travel from place to place, but the particles in a wave just oscillate around one location. So if you're far enough away from the shore, like if you're in a fishing boat or something like that, okay, or if you're in a pool, okay, you can sit there in an inner tube or in a small fishing boat and the waves go by, but you just kind of go up and down and up and down. You don't really go anywhere because as the disturbance happens, right, in this picture here, the drop hits the surface of the water, work is done by the drop on the surface of the water. That energy is then transferred from one to the next, to the next, to the next, right? And we just see this oscillatory motion. In the case of this fishing bobber, it kind of goes in a circular sort of motion, but it still ends up right back where it started. And that's what happens to the coils of this spring as well. They move, but they just move a little bit from there. They like oscillate around the place where they start, but eventually they end up right back where they came from. Okay? Go ahead.
Energy's not a particle, is it?
No, but, sorry. According to, at least as far as you're concerned, energy is not a particle, right? When you get into like string theory and stuff like that, and photons and things like that, then you can sort of think of it that way, but let's not go that far, so.
Not yet.
Okay, not yet. But that energy is transferred from particle to particle because when one moves, it runs into the next one. And then when the next one moves, it runs into the next one after that, and on and on and on. Good there? Okay. Question?
Huh?
Do you have a question?
No.
Sorry.
I kind of was last minute behind it.
Okay, that's fine. All right. How the particles move classifies what kind of wave that we create. So, this one here, this picture here, is generally what most of you think of as a wave, and that's basically what we were just doing, right? Hand moves up and down, vibrate under the spring to generate a wave, and as we discussed briefly, right, generating a wave requires work, right? Work needs to be done because I'm transferring energy from my hand to whatever is carrying my wave, right? And then that wave propagates away from the source. Propagates is just a fancy word for travels. Okay? So this is what most of you think is a wave. But if we look at the orientations, the wave itself, the disturbance, is traveling this way. But if we look at the spring or the string that is carrying that wave, it moves this way. Does that make sense? Right? The spring itself goes up and down as the wave is traveling from me to Cindy. Right? So when we have this perpendicular orientation of the way the wave is moving versus the way that the spring is moving, we call that a transverse wave. Okay? So transverse wave is the perpendicular orientation of the way that the wave is moving versus the way the spring is moving. All right? So, Cindy, we were doing this a little bit without knowing it. Okay? Okay, you want to grab the piece?
Wait, so the wave is moving that way?
Yep.
And then the spring.
Yep. Right? So the first one that I did, right, looked just like this, okay? And that's pretty easy to see, okay? And I don't know if you guys were watching before when we were doing it, but Cindy and I were kind of messing around, and we went this way, okay?
It's still perpendicular.
That's also a transverse wave. It's still perpendicular, right? Any orientation here is going to be perpendicular to the way that the wave is moving. So, you know, regardless of what line on the plane that is perpendicular to the floor, that makes sense. I just drew like a math term that you guys, right? Okay. They're still perpendicular to the way that the wave is moving. So all of these are going to be transverse waves. Okay? Good there? So, right, that then here a little bit more detail, right? It just shows that the one point, the red dot that's on that spring, if we were to put a red dot on this spring, you would see that it would go up and down, but at the end of the day, it's going to stay exactly where it's going to end up right back where it started. Okay? Does that make sense? All right. You ready for the other one? Okay. So here, let's grab our records. All right. So let's go over here on the side because this one demonstrates a little bit better. It demonstrates a little bit better on the floor. So if you want to readjust your position, you can. All right. So you can grab that. Alright. So if you would like to readjust your position so you can see. Good. There's lots of room over here. You can see the whole spring. Alright, so here we made a transverse wave in that small spring, and I can make a transverse wave in this spring too. I just caused it to swing like this.
That's cooler.
You like that?
Yeah.
Alright, anyway, but there is another way that I can do work on this spring. Alright? Here, I'm always going perpendicular. Oh, no, it's good. Alright, but I can do work on this spring in another way. Work just requires that I do force and distance. So in this case, I'm going to do force and distance, but instead of moving it perpendicular, I'm going to go straight towards Cindy. Right? You can definitely still see the wave going back and forth. More work. And if I continuously do that work, right, I end up with this. Okay. Does that make sense? Alright, so here, the spring is moving, and the wave is moving, but the way that the spring is moving is parallel to the direction that the wave is moving. Okay? I get a little bit of sideways work. Alright, so, say again.
Saw it. It wasn't.
Not right now. We can play this with you next week. Alright. So, that type of wave.
I've never excited such that
Alright. That type of wave, where the motion is parallel to the motion of the wave, we refer to as a longitudinal wave. We will sometimes refer to them as well. You might see them referred to as compression waves. Oh. You might see them referred to as compression waves. Okay? Again, we're still doing work, we're still applying a force, we're still moving that medium a distance to begin the wave, but now we're moving it parallel to the direction of wave movement as opposed to perpendicular. When we repeatedly do it, like I did at the end, Devin, what you saw was this happening, right? That as I push, I scrunch coils of the spring together, and that causes an area of compression. But as I pull back, I pull different areas of the spring apart. I actually do it the same thing, the same area of the spring, but because that compression then causes compression in the next part, that disturbance travels on. And so we end up with certain parts of the spring being stretched out in the expansion sections, but then certain parts of the spring being close together. So what you're seeing, and the reason the pieces of tape were on there, is because you can see that certain parts of the spring go expansion, contraction, expansion, contraction, expansion, because that's what happens when the wave goes by. Sometimes they're getting compressed, sometimes they're getting expanded back out. But at the end of the day, where does every part of the spring end up? Right back where it started, right? And that's what the pieces of tape on that spring are meant to show you. And like I said, you'll see that a little bit more when you do your lab this next week, okay? So, transverse waves, longitudinal waves. Go ahead.
So like solar waves,
Yep.
they'll go to an area, but then they'll go back.
Solar waves are different, okay? These waves that we just talked about here, I'm going to jump sort of to the end, right? I don't know why your book does this, but it does. There we go. So, these waves, the transverse waves, the longitudinal waves that we just demonstrated, we refer to generally as mechanical waves, right? So, mechanical waves travel through matter, right? This is the very last page of the packet if you're helping. If you're not, then that's okay. All right? We need certain waves, okay, certain waves need matter to transfer the energy one to the next, to the next, to the next, right? That's the difference between this ball directly carrying the energy from here to there versus the wave, particle, 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 right? But some waves, if you don't have the space filled up between the work, the original disturbance, and wherever we want it to go, that energy won't transfer. Sound waves are a great example of that. As your vocal cords move in your throat, they disturb the air around them. And then that air disturbs the next air, and that air disturbs the next air, and that's a sound wave is a mechanical wave because it needs something to travel through. If there's no air in this room, you don't hear me. Okay? Awesome, go ahead.
I have two questions.
Good.
First of all, is that kind of how electrical energy works then?
Electrical energy is a little different. Well, electrical, let's go with waves, even though electrical waves aren't exactly this, what we can't, it's not the correct term, they're called electromagnetic waves. Certain types of waves don't need matter to travel through. They're not mechanical waves. Like it says here, or it doesn't say here, we have electromagnetic waves that can travel through vacuum. We'll talk about those a little bit later on. Okay? Second question.
Oh, yeah. Does light travel in waves and if so they're transversal?
Light travels in waves. They are electromagnetic waves, so let's hold on to that discussion just for a second. Okay? Because light doesn't need matter to travel through.
Yeah.
We get our light from the sun, but there's nothing that fills the space between us and the sun. So those waves can get here even though they don't have a medium to travel through. Okay?
Okay, so sound waves come back.
Yep.
So I talk to
Echo.
you. Oh yeah, you hear it.
An echo is a reflected sound wave. All right. Joe, sorry. Go ahead. Go ahead.
So, for example, after the second of the light,
Yep.
there isn't any matter in space.
Right.
Isn't there actually dark matter?
Well,
Yeah, that's true. Like, what does that mean?
the thing about dark matter is it doesn't behave like other matter. So when light encounters matter, as we know it, there's three things that can happen. It could either be reflected, so it bounces off of the surface. It it can pass through that surface, refracted, which causes it to slow down, and we'll talk about that a little bit later on, or it can be absorbed, where that energy is just taken in by that substance and it doesn't give it off or let it pass through. Does that make sense? Well, more like
The human taking vitamin D from the sun.
no, more like in the auto. Say more like.
What are you talking about? What is he at?
Hold on, look, I get my brain is running too fast. So if we talk about it in terms of light waves, it would be something that is black. All right. Because I think we've probably learned before that black absorbs light, right? Okay. So nothing reflects off of that black surface. But if we're talking about sound waves, it would be something like carpeting or a soundboard or something like that. If you go into the PAC, right, what's all over the walls? Well, first what's on the floor? Carpet in the PAC, right? All the seats are upholstered, right? And then if you look at the side walls, you'll see that there are big squares of cushiony, carpeted sort of material, right? We don't want waves reflecting off the walls in the PAC. We'll talk about why that is a little bit later on.
Cushion absorbs it.
So the cushioning absorbs that
So
energy.
there's no
It
echo.
doesn't. Yeah, there's no echo in the PAC, right? Because echoes can mess up with the other waves that are going on, and we'll talk about why that is in a couple of days, right? But so yeah, that soft cushiony material absorbs that wave, right? Just like something like, whatever, a big pole vault mat, right, absorbs your energy from falling. Cushiony material on the walls or carpet on the walls absorbs that energy, right? Here, playing an instrument or singing in this room could lead to all kinds of weird things happening, and we'll talk about why that is later on.
Well, you absorb it, but won't it bounce back? Like how you sit on the bed?
It depends on how good of an absorber it is. You know what I'm saying? Like there are certain things that will absorb that energy and just hold on to it, right? Like, you ever see one of those stress balls that just like nothing?
And then
Like if
slowly
you just
goes back?
drop it, it just goes
flat.
like it doesn't bounce at all.
Or like a silly, or like a piece of Play-Doh.
Maybe silly Play-Doh or silly putty or something like that.
Silly Play bounces.
Yeah, I mean, depending on what shape it is. Yeah, Play-Doh or something like that. Yeah, Play-Doh is really good at absorbing all of that energy, right? So it depends on the properties of the material. Sometimes we want reflection off of that material, right? A mirror, right? We want energy, we want waves to bounce off of the mirror because that's what a mirror does, right? Joe, a little bit earlier, you asked about the speed of the wave. You mentioned something about speed. The medium that it travels through determines the speed of the wave in many cases. How fast I move my hand back and forth to create waves doesn't determine how fast they move through the spring from one side to the other. My hand would determine the frequency of the waves, how often they happen, but it doesn't determine how fast they move from me to Cindy. You ready?
Yeah.
Okay. This is getting into some stuff we're going to do the other. It just, so here. All right. So here, right, I make a wave, it goes down, it comes back, okay? It's hard to talk about the frequency of this wave because it doesn't happen again and again and again, you know what I'm saying? So if I continuously move it, right, we can talk about that frequency, okay? Let's go this way so you guys can see it better. Okay. So we can talk about the frequency of this wave, all right? Now, this is a special kind of wave called a standing wave, which again, we'll talk about a little bit around. Okay. But what's happening here is repeatedly, okay, I'm going to make a wave, then I'm going to make a second wave, right? So, but my second wave is going to not pass the other wave, but the first wave is going to get to Cindy's hand and start coming back towards me.
Oh, it cancels out?
Right. Well, it could, right? But more importantly, it just does this. They just pass right through each other. Okay? So if I create this wave and then I create another wave, it can't catch the first wave unless it starts coming back. Right? So the medium determines how quickly the wave travels. Right? So here, let's do this. Yeah. Yeah. So what? I mean, I guess kind of. I didn't make a point of pointing it out, but I guess it happened while we were doing stuff. So. All right, so here, Cindy and I are standing really close together, right? And so this spring is not stretched out very much, right? There's a lot of like loose play in this spring, okay? So if I create a wave, right, it does this, right? And then it dies out pretty quickly because it damps out because there's a lot of like energy loss to friction and stuff like that, okay? But more importantly, watch how long it takes to go from my hand to Cindy's hand, right? Ready? Okay? Even though technically this is the same spring, it is a different medium because I changed the condition of this spring. It's much more stretched out now, right? Now, when I make the wave, remember how fast the wave traveled? Like it's a short distance, but it was going back forth. Like it took. Yes, but watch how fast this wave travels, right? Ready? Definitely faster, right? Because the medium is different. So the condition of the medium determines how quickly things travel through. Okay? In actuality, waves generally travel fastest through solids. Because why? Well, all that is super close. So that boom, 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 that transfer of the energy from one to the next to the next to the next actually happens really, really fast.
Since waves travel, waves travel by different solids.
Yes.
So like, let's say, like you're like a complex, you're in a combat zone. Like
Yes.
Someone throws a grenade. Would it be better to jump like away, like over on the ground, or like jumping up the pond?
The pond, so the pond is actually better at damping things. One of the reasons why that waves travel quickly through solids, yes, the particles are really close together, but because of that, they actually don't lose a lot of energy when they run into each other, right? So if you've ever, like, if you watch old movies, it doesn't happen too much nowadays in movies, but have you ever, like, seen a Western, right? The idea that you can track somebody on a horse by listening to the ground. Like, have you ever seen? Happens in Lord of the Rings too, when they're trying to track them. They're trying to. Have you ever seen Lord of the Rings? The second one when they're trying to find the. So you can, because those waves travel faster through solids, but they also generally travel farther through solids because there isn't as much energy loss as the particles run into each other.
That's what rabbits do, right?
Yeah, I mean, well, snakes do it too. Snakes can feel vibration through the ground. Like, they smell with their tongue, but they also feel vibrations through the ground as well, because the ground actually transmits energy very easily, right? So a lot of times you can hear, or if you put your ear to a train track, you can actually hear the train coming from a lot farther away through the track itself than listening to the whistle.
So just stick your face on a train track.
Yeah. Well, one of the things that happens in like old Western movies is like, okay, if there's like a herd of cattle, obviously they have to make sure that the train isn't coming, because the cattle are going to get, as they're trying to go. All right. So you can do we put your ear to the track? Can you hear the train coming before you can maybe even see it or hear the whistle? Because that energy travels faster through the solid. A lot of times it travels farther, and that depends on the nature of the solid too. But so to go back to your question, water being a liquid actually absorbs a lot of energy, right? That's why we can dive into it off of the high dive, because it absorbs a lot of that energy as we fall into it. So the energy, like from a grenade or something, would definitely be absorbed by the water before it got to you, like if you were at the bottom of the pond or whatever it might be. Does that make sense? Right? It might travel faster, but it damps out much quicker because it gets absorbed and lost in friction and stuff like that. Okay?
What about a conch shell?
What?
A conch shell?
A conch shell?
Yeah, where you put it in your...
That is a lot of reflection, like because that surface is so smooth on the inside, that's why it sounds like the ocean, because you're just getting all that ambient sound that's reflecting back to your ear, because you know the inside of that shell is really, really smooth, and it reflects waves very well, so it kind of like gets in there and bounces around. Basically, yeah.
That's so cool.
All right, we'll pick this up on Monday. We may or may not start the lab on Monday. We can definitely do it Tuesday and Wednesday because we're on short periods again. So, yeah. Good job today, everybody. Much more engaged than the normal Friday. It's fun for me, just so you know.